So this video is going to be about using the oscilloscope to view the CanBus network and what sort of voltages you can expect from a functioning system. Your OBD2 port should have 16 pins, and they are arranged 1 to 8 along the wider side and 9 to 16 on the shorter side. These are universal, so terminal 4 will always be battery negative, terminal 16 will be battery positive, and then your CAN high will be terminal 6 and CAN low will be terminal 14, and we're going to use terminal 4, the battery negative, as our common ground for when using our oscilloscope for measuring the CAN bus. So if we go into 4 and 16, we should get battery voltage. And with the vehicle shut down, if you take the resistance across CAN high and CAN low, so that will be terminal 6 and terminal 14, you should get 60 ohms, and that is because of the two 120 ohm resistors either end of the network that are in parallel. So while we're here, we'll just quickly measure the voltage on CAN high. So we'll leave our red probe in terminal 6 and we'll just put our black probe back into battery negative, which is terminal 4. The voltage on CAN high goes between 2.5 and 3.5 volts, so we should get an average reading of that of around 2.6 volts. And now we'll just measure the voltage on CAN low, and so the voltage on there goes between 1.5 and 2.5 volts, so we should get an average reading on there. And both those voltages added together should equal 5 volts. So I've got channels 1 and 2 of the oscilloscope connected to two banana style connectors, and we're just going to connect the negative of channel 1 and 2 together, and that will go into our negative terminal 4 of our OBD2 connector. And then the positives of channel 1 and 2 will go into CAN high, which is terminal 6, and CAN low, terminal 14. So our negative for channel 1 and 2 can go into terminal 4. Channel 1 can go into CAN high, terminal 6. And channel 2 into CAN low, terminal 14. So I've got channel 1 and 2 at 500 millivolt divisions, and I've got the time scale at a 10 microsecond division. Now each of those square waves represent either a binary code 1 or 0 or several 1s or 0s depending on the width, and the reason there's two voltages, two lines used, is to reduce errors occurring from interference, as it's the difference in voltage between CAN high and low that is translated into a 1 or a 0. If the difference is 2 volts, it means it's a binary 0. If the difference is 0 volts, it's a binary code of 1. The other thing we can do here is see how fast this network is, so we'll just press measure on the oscilloscope and then go to cursor and time, and we'll just move cursor B to one end of the shortest bit we can see there, and A to the start of that, and we can see that one bit is 2 microseconds in length. So if each bit is 2 microseconds in length, all we need to do is find out how many of those 2 microseconds is in 1 second. So if we divide 1 by 2 millionth of a second, we will get 500 kilobits per second. So what we'll do now then, we'll just use the voltage cursor measurement on the Owon oscilloscope to measure the CAN high voltage. So CAN high will start at 2.5 volts and go up to 3.5 volts, and CAN low will start at 2.5 volts and go down to 1.5 volts, but they both sit at 2.5 volts in their recessive state. So when there's 0 volt difference, it's a binary 1, and when there's a 2 volt difference, it's a binary 0. So the last thing we're going to do then is we're just going to use one channel on the oscilloscope and compare the voltages from CAN high and CAN low and see if we can see that interference-free binary code, so the difference in the voltage between both of them. So we know the difference is going to be 2 volts, so we've got 2 volts per division, and we know each bit is 2 microseconds in length, so we've got the time division as 2 microseconds.